Everyone, hello and welcome. This is our lecture on Appendix G, G1 and G2, which is talking about exponents. So here I've got some exponent rules. We've got exponent rules when we have a common base, and we see what we can do when we have a product of things with a common base, and then when we have these things inside parentheses, and then what happens when we have a quotient. Also, I'm an idiot. I don't know where my glasses are. These are my prescription sunglasses, and this is the only way I'm going to be able to do this without having memorized all the slides. So you have to forgive me. Okay, so here we have a to the n times a to the m, and what do? We just add the exponents, keep the same base. So this would be like x squared times x to the fifth. Well, if we have x squared times x to the fifth, that would be x to the 2 plus 5, or x to the 7th. And the way that we know what we've got here is, well, a to the n literally means we have a times a times a times a n times. So you could write out the example I gave you, x squared, x times x to the fifth, x times x times x 5 times. And then you'll see, oh, we got 7 x's, so that's x to the 7th. You can do the same thing to illustrate this quotient one, where we have a to the n divided by a to the m. That's a to the n minus m, right? So a to the n minus m. You stop here, put a star by this. We'll come back to this. A little bit later on, I'll talk about what do we do when we have negative exponents. Well, if you combine the idea from how we deal with negative exponents and how we deal with fractions and products here, you'll see that the rules come together nicely. You can deal with this quotient rule as multiplying or as a product of terms where you have the same base, but one of them has a negative exponent. Well, that doesn't make any sense now. We're just staring at this, but when we get to that in the future, remember, you can come back and you can recast those rules in terms of what we do in the future. Okay, and then the last one is what happens if you have some a to the m to the n. So what do we do then? If we have these parentheses, then you multiply the exponents together. So the example would be, suppose you have x squared to the third. Well, remember the thing in the parentheses, x squared, that tells us we have like x times x twice. And then the exponent outside the parentheses tells us we have 3 x squares times each other, or 3 times the collection of x times x. In here, in the most general version, that a to the m tells us we have a product of m a's, a times a times a, m times, and then that collection of m a's we have multiplied n times. And that's why we have a to the m times n for the exponent. Okay, so to make sense out of those, best thing to do is just write down some examples, use x squared, use x to the third, x to the fourth, simple ones like that. These things work for numbers too. The bases can be numeric, so a good one to work with would be 2's. So like 2 to the fifth, 2 to the third. Why? Because hopefully by now you've memorized the bases of 2. So 2 squared is 4, 2 to the third is 8, 2 to the fourth 16, 2 to the fifth 32, and so on and so forth. So you could use those. Okay, so suppose we have expressions with a common exponent like these. So suppose we have this collection ab to the n, right? What do we do now? Well, it's not quite distributing, but you can attach that exponent to everything inside the product. And a really key thing to make sense out of here is that, look, this is multiplication. This is not addition. This is a multiplication here. And what this AB, this product, is doing, well, it's being multiplied by itself n times, right? So think about if this was AB to the second. Well, then what we'd have would be the product AB times the product AB. So actually write that out on your paper. And then you'll see, because multiplication is commutative, we can go a times b, and rewrite that as a times b times b. And when you do that, you'd have, oh, a squared times b squared. And on a smaller scale, that's exactly what this general one is doing for any n. And the same thing for the fraction. The same thing for the a over b to the n. What we literally have there is this fraction, a over b times a over b times a over b n times. Remember, you multiply numerator to numerator, denominator to denominator. That's why we have a over n, a to the n divided by b over n, or b to the n. Okay, That's why we have a to the nth power divided by b to the nth power. All right. So suppose we have 0 and negative exponents. So in this case, suppose we have a 0 exponent. Well, anything to the 0th power is just going to be returned as 1, right? So x to the 0 is 1, 2 to the 0 is 1, a million to the 0 is 1. All right, what about to a negative exponent? Well, if you have a negative exponent, what that tells us is that we can rewrite that as a positive exponent and put it in the denominator of a fraction. Now, it's really crucial here that you recognize what's happening is the negative sign is only attached to the exponent, and the negative sign is only indicating that we have that base with its exponent in the denominator. So it's not, we're not attaching that sign to the base, we're not distributing the base, nothing like this whatsoever. So if you have, for instance, 2 to the minus second, so 2 to the negative second power, we rewrite that as 1 over 2 squared, or 1 over 4. Notice that's a positive 1/4. It's a positive 1 over 2 squared. If we have 1 over x to the third, we'd rewrite that as what? Well, the x to the 1 over x to the third, because x to the third is in the denominator, we can bring it into the numerator by writing it as x to the negative third, right? So basically, the negative exponent, wherever it's appearing in the fraction, it's just telling us that we can make that exponent positive and then move that thing to the other part of the fraction, wherever it's got to go. So if you have negative exponents in the numerator, you make it positive and put it in the denominator. If you have negative exponents in the denominator, you make it positive and put it in the numerator. What are we making positive? Only the exponent. The sign of the base doesn't change. Okay, so this is the part where I was saying you can relate this to what we were doing previously, where we had these rules here. These right here. You can recast multiplying by a term with a negative exponent as a fraction. And so work through that on your own. There's a cool insight there, and I think that's actually something that's maybe better for you to figure out on your own sheet of paper. The learning value is greater if you just follow the guidance I've just given you and now work it out for yourself. Obviously follow up with me if you can't make it work or if you have questions. So I'll be available for office hours. Okay, what about fractional exponents? Well, suppose you have a to the 1 over n. This we just write as the nth root of a, or a to the m over n, the nth root of a to the mth power. Okay, well, one thing you could do is you could always memorize these, right? So if you want to invest the time, if you're good enough memory, you can memorize this, then great. What I do is I just always remember that a to the 1/2 power is the square root of a. So when we have a square root, when it's just a regular radical, when it's a regular square root radical, we never write that 2. But implicitly, that 2 is right there where this n is, right? So a to the 1/2 is the same as the second root of a. Okay, so if you use this, you can remember, oh, wait a second, whatever is the denominator, that goes into the little sort of crux of the root. And then whatever is the numerator of this fraction, that's going to end up going to be this power right here. So if you have a to the 1/2, this is like the second root of a to the first, right? Anything raised to the first power is just that base. So 1 to the 1th is just 1, 2 to the 1th is just 2, 3 to the 1th is just 3. Common mistake is that people will say, oh, x to the 1 power is 0. No, it's x to the 0 power is 1. 2 to the 0 power is 1. Anything raised to the first power is just itself. Because remember what the powers are doing, what the exponent is doing. It's saying, I have as many instantiations of that base as the exponent tells me, multiplied by each other. So if you have 2 to the second, that's telling me I have 2 times 2, or 4. If I have 2 to the third, that's telling me I have 2 times 2 times 2. If I have 2 to the first, that's saying I just have 1, 2. Right? So that's what's going on there. Okay. So here's an explanation of the exponents a little bit more clearly. So this is what I've been saying verbally. Now here we can see this visually as well, right? So suppose we have this rule a to the n times a to the m, right? This just means we have n factors times m factors. And if you look at this, oh, this is a to the n plus m factors. So here's an example with q's, and q to the 5th, and q to the 7th, and q to the 12th. And like I said, this can work for q, this can work for x, any letters, any numbers, whatever we'd like it to be for our base. Okay. All right, so one really useful application of this rule is to be able to write the power, whose exponent is a sum, into a product of powers. So suppose we have some base, and we have an exponent that's a sum. We can rewrite this as what? Well, we have 5 to the 2 plus a. We can rewrite this as 5 to the 2 times 5 to the a, or as 25 times 5 to the a. We can rewrite x to the r plus 4 as x to the r times x to the 4th. Okay, so you're staring at this and you're like, well, why would I ever want to do this? It looks nicer the first way. Well, this is useful, and this is my comment down here. It's useful in the case of if you have to cancel something. It's also useful. It's also useful in particular cases where we're trying to simplify something down, and we want to be really clever. This particularly is useful when you're talking about logarithms and the exponential function. So being able to go back and forth between these rules is super important there, because what we can do is we can rewrite a particular term in an equivalent but more convenient way to work with, and that's what this rule buys for us. Okay. All right. So here's another comment. When we divide powers with a common base, we subtract the exponents. Here's why. It's a canceling story, right? So 5 to the 6 divided by 5 squared, 5 to the 6 over 5 squared, is written as 5 to the 6 minus 2. We subtract the denominator from the numerator minus denominator, 5 to the 4th. Why? Well, let's just write out 6 5s divided by 2 5s. And what can we do? We can write this as, oh, I should have, what did I do? You can see my mistake. I should have canceled off another 5. All right, so I meant to cancel off. I canceled off 2 5s in the numerator, and I've only crossed off 1 5 in the denominator. I'll fix this for the slides on Canvas, right? So this right here should be crossed off as well, right? So don't try to cancel and have just 5 times 5 times 5. It's not 125. No, we have 4 5s here because I tried to cancel 2 from the numerator. I only canceled 1 from the denominator. I should have fixed that. Well, I will fix it. Okay, so here's another example. This one, did I do it right? I did, right? So here, pi to the 3rd, 5 to the 5th. Pi to the 5th divided by pi to the 3rd is pi to the 5 minus 3. That's pi squared. All right, here's why it's a canceling story. And it works just as well if our terms are sums. So we have the quantity c plus d to the 4th divided by the quantity c plus d to the 3rd. We just cancel off the product, right? Because c plus d to the 4th, what that literally means is c plus d times c plus d times c plus d times c plus d divided by 3 of those, right? So that's what we have. You might be tempted to try to do some type of foiling. Well, we can't do that because here we've got c to the 4th. Here we've got c to the 3rd. I mean, yeah, if you wrote this out as a product, sure. If you really wanted to expand this, that's how you do it actually. You'd FOIL these right here, and then you'd FOIL these, and you multiply those things together, or you'd use the extended distributive property or whatever. Clearly, that's not the best approach here, right? Here we just want to cancel things off. All right. So here is another example, rewrite expressions of the quotient. So basically, we're using the property in reverse. So suppose we have 10 to the 2 minus k. What does this want? This says that we have a base of 10, 10 over 10, and then what are the exponents? 2 minus k. So that's this right here. And this works with an expression that's a sum, so p plus q to the a minus b. Oh, that's p plus q to the a divided by p plus q to the b. All right. Raising a power to a power, so if we have a number in exponential form, raise it to a power, we can multiply exponents. So we saw this as just an example of the rule we saw previously. So 7 squared to the 3rd, that's just going to be 7 to the 6th. Right. Okay. And you see here I'm making use of the intermediate rule, the first one we introduced, which is just that a to the m times a to the n is just a to the m plus n. That's what we did right here. Okay, and then 5 to the p to the third. Well, this third here tells us that I've got three 5 to the p terms that are multiplied by each other. They all have the same base, so I'm going to have 5 to the p plus p plus p, or 5 to the 3p. Okay. Here's one more comment. Suppose we have 2 to the x, that thing to the x. This tells us we have x collections of 2 to the x, and that's what this is right here. All right. Here's a note. Note 2 to the x squared means 2 raised to the x squared power, not 2 to the x raised to the second power. Right? This is 2 raised to the x squared power, not 2 to the x to the second power. Okay, of course, the second phrase is written instead as 2 to the x squared, and is equivalent to 2 to the 2x. Okay, so just a point of clarification. All right, if we have a to the m times n, we can write this as a to the m, that quantity, to the nth. So 2 to the 3 times 2, we can unpack and rewrite this as 2 squared to the third, or 4 to the third. All right, so e to the 4t, we can write this as e to the fourth times t, or e to the t to the fourth. And this last comment right here, this is super important, exponential functions. So if we're working with logarithms, if we want to take logs of both sides or something like that, this is really useful. Okay, so expressions with a common exponent. So suppose we have products and quotients raised to the same exponent. So we have 5 to the second times 4 to the second. Here we have different bases, right? Well, what do we have to do? We can expand 5 times 5 times 4 times 4, and then write that quantity, 5 times 4 squared. So 20 squared. We can also go in reverse, so we have 10 squared. We can write this as 2 times 5 squared. And then we can not distribute, but we can sort of make sure that each of the terms of the product receives that exponent. Okay. So here's some examples. Rewrite without parentheses. QP to the fifth, 4ab squared to the third, 2x to the 2nth times, raised to the 3nth power. Okay, so stop the video, go ahead and give it a try. And here's the result. For each of these, what's the way to see this? Well, as much as possible, try to write out what's going on. You don't have to write all the terms, especially when there's like 3 to the n, but write enough of the terms and then use the label with under brackets to show what your collection is, and that can kind of spell out exactly what we're doing here. Okay, so here, oh, geez, I forgot to change this. So this is q to the p to the q to the 5 times p to the fifth. So this should be jeepers. So this should be yeah, q to the 5 and then p to the 5. And then over here, what's this? Oh well, we're going to send this 3 through. So 4 to the third, a to the third, b to the sixth. Right? Okay. And then over here we have, 2 to the 3n, and then we have x to the n to the 3n, and then using our rules we have 8n, and then we have x to the 6n squared. Okay, yeah, so clearly I'm going to fix this, right? This should be q to the fifth and then p to the fifth. Okay, and then over here, so we can collapse expressions down to be written as a single exponent, so a to the third, b to the third. So here we have a times a times a, b times b times b. That's just a, you know, we can use the commutative property of multiplication, put a's and b's next to each other, and then write this as the quantity a, the product a times b to the third power. And same thing here with 9 to the y, 9 times y squared, or 3 squared, y squared. And here, similar sort of thing. Okay. Suppose we're dividing two powers with the same exponent. Well, look, 2 to the fourth divided by 3 to the fourth. We can't use the rule, right? We can't write this as 2 to the 4 minus 4. It doesn't work. Why? Well, these are not the same base, right? This is 2, and that's 3. So how do we do this instead? Well, let's write this out. Literally 2 times 2 times 2 times 2 divided by 3 times 3 times 3 times 3. So then we can get a sense of what this product is. Oh, well, you know, it's 2/3 raised to the fourth power. So here's the more general rule. A over b to the n is, well, a to the n over b to the n. Well, that was our rule from before. So, All right, so we can rewrite without parentheses. Well, let's distribute, or not distribute, let's inherit. Let's allow our 3 to inherit this 2 and our 4 to inherit that 2. And so we'll have, what, 9 36s. Or 9 16ths. I had the 6's in there. Okay, so then we have 2p to the, over 3q to the third. So, right, so the first thing I'm going to do is I'm going to allow these parentheses to remain. And that's just going to help me be really careful to make sure that this 3 goes to each of these 4 characters, to the 2, to the p, to the 3, and to the q. So there we go. So then 0 and negative exponents. So, well, a to the n divided by a to the n. That's a to the n minus n. That's a to the 0. Well, that's 1, right? So clearly, why do we have 1? Well, we know a to the n divided by a to the n. That has to be 1. Here's sort of the explanation for why. Okay. So suppose we have a to the 0 divided by a to the n. Here's where the negative exponent's coming from, right? So a to the 0 over a to the n is 1 over a to the n. So we define a to the minus n as equal to 1 over a to the n. So what's the summary? Well, remember the negative exponent is just telling us to change the sign of the exponent, not the base, and take the reciprocal, not to make the number negative. So evaluate the following: 2 to the 0, to the minus 1, 3/4 to the minus 1. All right, so stop the video, give it a try. Well, 2 to the 0 is just 1. 2 to the minus 1, this just tells us we need this base of 2 to be in the denominator of a fraction raised to the 1 power. Right, 2 raised to the 1 power in the denominator of a fraction. So this is 1/2. And then this is saying we want 1 over 3/4 to the 1 power. Well, 1 over 3/4 is the same as 1 over 1 times 4 over 3, or 4/3. So here's just that mathematical explanation. All right. I'm going to sit forward a little bit. I'm worried that this might be causing some scratching. So the next thing we're thinking about is radical expressions. So we're thinking about roots. So suppose we have square root of a. This is the positive number whose square is a. So square root of 25 is 5, is just telling us the same thing as 5 squared is equal to 25. The cube root of a is written as just radical sign with a 3 over a. And for example, we know the cube root of 27 is 3 because 3 cubed is 27. Okay. In general, the nth root of a is the number b such that b to the n equals a. So if a is negative, then the nth root of a exists when n is odd, but is not a real number when n is even. Let's make sense of that statement by looking at some examples. The cube root of 27. Let's see. So we have. Let's see. What do I want here? I want minus 3 raised to the third. Minus 3 raised to the third is 27. I've got a mistake here, right? Why do I have a mistake here? What should this be? I have to fix this. So minus 3 to the third power, that's telling us we have minus 3 times minus 3 times minus 3. 3 times 3 times 3 is 27. So that part's right. But we have a minus 1 times minus 1 times minus 1. Well, the first two minus 1s signs cancel and make it positive. So we have a positive 1 times the remaining minus 1. That's a minus 1. So this here should be minus 27. Okay. And then square root of minus 9, that's undefined. There's no real number whose square is minus 9. So, right. So here we're saying, is there a real number whose cube is minus 27? Yeah, sure, minus 3. Is there a real number whose square is minus 9? No. Okay. So evaluate square root of 121, square root of minus 32, square root, fifth root of minus 32, fourth root of minus 16. Okay, well this one you should know. This one, what are we looking for? We recognize a negative and we see an odd. Negative, we see an even. So this one's got to be undefined. This one's going to work, and this one's 11. So 11. Here we just need the number whose fifth root is negative 32. So minus 2 to the fifth is minus 32, so the answer is minus 2. There's no number for which the fourth root is minus 16. One way to see this is we can rewrite this with, we can rewrite the fourth root as just square square, and we know it doesn't work for, there's no, we know the square root of a minus number is not a real number. These imaginary numbers, and we're not going to worry about that here. Okay, so we can use fractional exponents to describe roots. So here we're just using our laws of exponents. So a to the 1/2 squared is just a to the 1/2 times 2, or a to the 1, or a. What's this telling us? This is saying the square root squared is just the base. The square root of a squared is just a. Right? So we know this already. Root 2 squared is just 2. Root 5 squared is just 5. Root x squared is just x. Similarly, square root of 2 times the square root of 2 is 2. That's just square root squared. Square root of 5 times square root of 5 is just 5. That's just square root of 5 squared. Square root of x times the square root of x, that's just x. And this is going to be really important when we're rationalizing the denominator in a little bit. Okay, a to the 1/2 is a number whose square root is a, and we conclude a to the 1/2 is square root of a. Cool. More generally, if n is a positive integer, then a to the 1 over n times n is just a, right? So what's this saying? That's saying a to the 1/3 to the third. Well, use our exponent rules. A to the 1/3 to the third is a to the 1/3 times 3, or a to the 3 over 3, or a to the first. So that's just a. Okay. So let's try out our exponential laws on fractional exponents. 16 to the 1/2, 25 to the minus 1/2, 64 to the minus 1/3. Is this legal? Well, sure, this negative is attached to the exponent, not to the 25. So 16 to the 1/2, that's the square root of 16. It's 4. Square root of 25. Oh, this is 1 over the square root of 25, right? And then right here, this is the cube root of 64. And indeed, that's what we've got. Okay. So suppose we have our exponent rule, a to the n times, or a to the n to the mth, a to the n times m. This defines our meaning of fractional exponents, in which the numerator is not 1. So for instance, we can think of a to the 2/3 and 25 to the minus 3/2. How can we rewrite this? Oh, a to the 2/3 is just a squared times 1/3, or a squared to the 1/3, or a squared to the cube root 3. So, or a squared, the cube root of a squared, or the cube root of 64, which is just 4. Here's another way to write this. 8 to the 1/3 times 2, or a to the 1/3, or the cube root of a squared, or 4. Why? Because the cube root of 8 is 2. Okay. And then we can do the same thing with 25 to the minus 3/2. And then in general, of course, this is just our rule from before. A to the m over n is just the nth root of a to the m. Okay. Suppose we have a product a to the 1 over n times b to the 1 over n. Well, we can write this as ab to the 1 over n. They've got the common, basically what's the rule? Doesn't matter if you have fractional exponents or if you have integer exponents. If you have the same exponent, you can pull that off of those. Think about what's happening. This is sort of the reverse of our rule. So think of like ab to the 1 over n. We distribute kind of, although that's not the right term, you distribute kind of that 1 over n to the ab. Here we're pulling it back. So here we have a to the 1 over n times b to the 1 over n. Here we're going to pull off that 1 over n root, and we're left with just that product, a times b, that thing to the 1/n. That's this right here. All right, so simplify these expressions. What do we want to do here? Well, the first thing we can recognize is, hey, this is the same cube root. So I can write this as what? Well, first it might be helpful to rewrite this as fractions. So you can write the cube root as to the 1/3, and then it's real obvious to use the rule from the previous page. So we'll just have 2 times 4 to the 1/3 power, or 8 to the 1/3, or 2. And you could think of something a little bit similar with this other one. What do we do for this other one? Well, I'll write this as z to the 6th, w to the 9th to the 1/3, and then I'll just distribute this 1/3 to each. I have z squared w third. Okay. This is just a summary slide. I don't want to read through this, but this is basically sort of summarizing what's going on with roots as fractional powers. Basically, the idea is that we can think of roots as fractional powers, we can think of fractional powers as roots. When do we want to use one or the other? Whenever it's convenient, right? So you just want to be comfortable working interchangeably with square roots versus to the 1/2 power, with cube roots versus to the 1/3 power, so on and so forth. Okay, so the next thing we want to do is think about combining radicals. The basic intuition here is just that you can treat the square root of something, you can just treat that as one entity, one object, and then use all your intuition from combining like terms here. So I think the example I have is 2 to the 5th plus 9 to the 5th. Well, just think of 2 to the 5th. 2 times the square root of 5 plus 9 times the square root of 5. You can just think of this as 2 times something plus 9 times something. All right, so that's 11 times something. What's that something? Square root of 5. So it's 11 square root of 5. All right. And same thing here. We're just collecting like terms. In this last one, we have root 5, we have minus 5 times square root of 5 plus 8 times the square root of 20. When I have something like this, basically what I'm going to do is I'm going to look and see, is there some square here that I can take out in order that maybe I might have a common root factor. So for instance, I can write 8 root 20 as 8 times square root of 4 times 5, or 8 times the product of the square root of the product 4 times 5, or 8 times the square root of 4 times the square root of 5, or 8 times 2 root 5, or 16 root 5. And I can use that to simplify the expression from above. Remember, it was minus 5 times square root of 5, now plus 16 square root of 5. That's just 11 square root of 5. And then the last thing, rationalizing the denominator. Basically, the idea with rationalizing the denominator is that we don't want to have radicals in the denominator. We want to have all the radicals in the numerator, if at all. Well, if the denominator is just one single radical, all you need to do is multiply by 1 written cleverly, so that you have that radical times itself, which just removes the radical. So for instance, if I have 1 over the square root of 2, how do I rationalize that denominator? Well, I'm going to multiply 1 over the square root of 2 times root 2 over root 2. Why? Well, root 2 over root 2 is just 1. And then I'll have in the denominator root 2 times root 2, that's 2. And the numerator, 1 times root 2. Okay, so once again, here's the example. Suppose I have 1 over the square root of 2. I want to rationalize the denominator. I'll just multiply top and bottom by the square root of 2. Then the numerator will inherit the square root of 2 term, and the denominator becomes root 2 times root 2, or just 2. So the answer is root 2 over 2. Well, suppose you have something more complicated. You have a sum, or a difference. Now what we're going to do is we're going to exploit the idea of a difference of squares. Why a difference of squares? Well, if we get a difference of squares, remember, the middle term drops out, and we're just left with something squared minus something else squared. Well, if one of those two somethings, or the something else, is a radical squared is just whatever is the base. Right? So if we do this carefully, we can eliminate radicals from the denominator. That's going to be our strategy here. Okay, so suppose we have the square root of 2 divided by 2 plus the square root of 2. Let's focus on this 2 plus square root of 2 term. Remember, we can make a difference of squares. What would this involve? Well, we want 2 plus root 2 times the product 2 minus root 2. And if we do this, we'll get 2 squared minus root 2 squared. And that's 4 minus 2, or just 2. So it's beautiful. So that's exactly what we want to create. That's the idea of a difference of squares. Why? When we use FOIL, the middle term drops out with a difference of squares, and the root term, for example, just for the sake of argument, root 1 times root 1 is just 1. Yeah, it's also 1 because square root of 1 is 1, but for the sake of our argument here. Okay, so rationalize this denominator. Let's multiply top and bottom by 2 minus root 2. right? So this 2 minus root 2 term over 2 minus root 2, that's just 1. This doesn't change the value of the proportion. And now I'm going to have to distribute this to each of the terms on the top, and I'm going to have to FOIL the bottom. When I do this, this works beautifully. So here's the top. I just use some parentheses. I don't know if that makes it easier to see what's going on or not. I hope so. Square root of 2 times 2, square root of 2 times minus 2. Well, I'm going to get 2 root 2 minus 2. Why? Because root 2 times root 2 is just 2. In the denominator, I'll get, well, it's a difference of squares. So I'll get 2 squared minus root 2 squared. Well, that's perfect, because I'll have 2 squared is 4, minus root 2 squared, that's 2. I'll have a 2 here. Now I'm realizing I've got a preponderance of 2's. So what do I want to do? I'm going to factor out a 2, and I can cancel. I actually should have put a canceled here, because that's what I'm ultimately going to do. Really, I should probably factor out a 2 first. So if you factor this thing, you'll have 2 times square root of 2 minus 1 divided by 2. And then you cancel those 2's, and you're left with root 2 minus 1. Okay, very good. Well, so let me know if you have any questions, and sorry about the sunglasses. Hopefully I find my real glasses at some point. I'm going to put these back on so I can figure out how to stop this video.